Thank you very much for the introduction, and also thank you to the organizers for putting together the workshop and the invitation. I'll be talking about the uniqueness problem for space-time extensions. Let me start with a very classical introduction to this problem, and let me first talk about the extension problem and something you will all be familiar with. And this is the extension problem for functions on RD. So the setting is that you have some subset A of RD, and you have a function which is defined on this subset. And now a very classical problem is, can you extend this function f to a function capital F, which is defined on all of Euclidean space RD, such that this function agrees on the subset A with the prescribed function f. And this is, of course, there's a rich literature on this problem, and the solution depends, of course, on the set A, for example, regularity of the boundary and so on. It also depends on the regularity of the function f, which you prescribe, and the capital function f, the regularity of the extension. So I don't want to talk that much about the extension problem, but what I want to talk about is the uniqueness of the extension problem. And in the setting for functions on RD, this is a trivial problem, at least for continuous extensions. So if the extension capital F exists, and if it's continuous, and since f is an extension of little f, so in particular also little f is continuous, then, of course, just by continuity, when you take a sequence of points to the boundary, the extension capital F at the boundary, so at the closure of A, is uniquely given. So if you have two continuous extensions, then they have to be the same on the boundary. And this is what I would like to refer to as uniqueness of continuous extensions for this extension problem for functions. So this talk is concerned with the analogous problem for extensions of Lorentzian manifolds. And so here, Mg is a Lorentzian manifold, gamma is a regularity class. So here, for example, continuous, local Lipschitz, or smooth. And then let me first tell you what the analog is of an extension of a function to all of RD. So here we extend a particular Lorentzian manifold to a bigger one. And so a gamma extension of Mg is an isometric embedding iota, which embeds the manifold, the function little f we start with, into a bigger one, M tilde. Here where M tilde, G tilde is a Lorentzian manifold of the same dimension as M. And now the Lorentzian metric, G tilde, is gamma regular. And I also assume that the extension is non-trivial. So I do have a non-empty boundary of M in M tilde. And so let me now tell you what the uniqueness problem of the extension for Lorentzian manifolds corresponds to. So here we have our Lorentzian manifold we start with, Mg, and I have two extensions, gamma extensions of a certain regularity of this Lorentzian manifold. And here, so I do have the boundaries. And the question now is whether the extensions agree here on the boundary, like on the point of the boundary or segment of the boundary. And this is already much more difficult to formalize, since, of course, I don't have an a priori identification of a point here on this boundary and a point here of this boundary, since these are points in different manifolds. And so the way you would formalize whether you do have uniqueness of the extension at the boundary is that you look at the identification map. And so the identification map, here denoted by id, is that you identify the image of M in this extension with the image of M in this extension just by going up by iota tilde and then going down by iota hat. And so now you can ask whether this identification map extends as a suitably regular isometry to the boundary. So here we have this isometric identification of this shaded set with this shaded set. Does this isometric identification extend to the boundary? And so when you think about, so I said whether it extends as a suitably regular isometry to the boundary. If you think about, I already have that the identification map here and here is an isometry, which means that if I pull back the metric from here to there, so if I have the pullback of G hat, that this is G tilde, if I express this in coordinates, then of course, if G tilde is continuous, G hat is continuous, and if the pullback extends as a C1 diffeomorphism, then just by continuity, since it's an isometry here and here, it will also be an isometry on the boundary, just by continuity. So this already shows that the problem of the uniqueness of the extension is actually a problem of uniqueness of the extension of the differentiable structure, namely whether I can extend the identification map as a suitably irregular diffeomorphism to the boundary. And then I already get that it's an isometry at the boundary. Another way of seeing this is that if I already know the extension of the differentiable structure, so for example, if I look at this extension and I delete the metric here in the extension, then there's only one way to extend the metric continuously. This is just by taking a point here at the boundary, taking a small chart, and then with respect to this chart, I can write down the components of the metric here as continuous functions, and then by the previous result that continuous functions extend uniquely to the boundary, I know that if I have a continuous extension of this metric on this background manifold, then it is unique. So this shows that this problem is actually a problem about extension of the differential structure. Yeah? And this is what I just said. So our extension of differentiable structure is equivalent. So does the identification map extend as a suitable regular diffeomorphism to the boundary? And to preempt any confusion, let me also say that here we only look at the uniqueness up to the boundary and not beyond the boundary. If you want to get uniqueness beyond the boundary, of course, you need to impose some equations like the Einstein equations or something like that. What's the motivation? So for me, certainly it's a fundamental problem in Lorentzian geometry, like analogous to the extension problem for functions. Then another motivation for me is the question whether low regularity extensions to weak singularities are unique. So for example, when you look at the interior of black holes, so if you look at the interior of a rotating black hole, then generically we expect that there will be a weak null singularity forming at the Cauchy horizon, where the metric indeed extends continuously, but you don't have an extension as a weak solution to the Einstein equations. So this is a singularity which is weak in the sense that you have a continuous extension. And then, of course, the question already is, do these extensions, are they actually unique or not? So this motivates the investigation of this problem. And another more immediate motivation for me to carry out this research is that I also need such results to prove low regularity and extendability results, in particular Lipschitz and extendability results for such weak null singularities. So let me start with something classical now, namely tell you that in general extensions of Lorentzian manifolds, even if they're analytic, are in general not unique at the boundary. And this is something I think most of you will be familiar with. So this is the very easy example to present is the Misner spacetime. And so this is this product, this Lorentzian cylinder, where you have the time coordinate here on this interval and an angular coordinate here on the S1. And this is the metric. And so I've drawn here the spacetime, and I've drawn for you also the past left-going null GD6, which are blue, and the past right-going null GD6, which are red. And we have this behavior that they wrap infinitely often around this S1, and they accumulate here at the a priori singular boundary at t equals 0. And so now you can extend past this coordinate singularity in two different ways. The first one is that you stretch out or straighten out the left-going past null GD6, the blue ones. This is by doing this coordinate transformation, and the metric takes on this form here, which is clearly analytic and extends beyond t equals 0. And this is this picture, which I've drawn here, and you'll see that here the past left going null GD6, they cut right through the S1 at t equals 0. While the right-going null GD6, they still accumulate at this hypersurface. And similarly, you can take a different extension in which you straighten out the past right-going null GD6. So we have this picture, and the situation is reversed. So now the right-going null GD6, they cut right through, and the left-going ones, they accumulate at the S1 here at t equals 0. And so, yeah, we see that we have two extensions which are even analytic, but they are, have different extensions beyond the boundary at t equals 0. And you can already see this, from the picture that here, these null GD6, they have a limit point at the boundary, while in this extension, they don't have a limit point, but they accumulate on the whole boundary. But to use the framework which I introduced earlier in terms of the identification map, we can also see this here explicitly. So I write down the identification map from this first extension m tilde to m hat, which means I express here the TU coordinates in terms of the TV coordinates. And this is just, so the identification map with respect to these coordinates takes this form. And we see here that when t goes to 0, the identification map does not have a continuous extension to the boundary since this goes to infinity, which captures that the singularity, that the null GD6 wrap around infinitely often. So you can say, okay, is there no way in which I can get uniqueness for the Lorentzian extension problem? And the answer is that you can still get some uniqueness properties. And to the best of my knowledge, these uniqueness properties, they were for the first time systematically investigated in a beautiful paper by Piotr. And so let me tell you what he proved. So he started with a smooth d plus one dimensional Lorentzian manifold. So here we need to assume that we are at least in 3 space-time dimensions for a reason which I will come back to shortly. And so here we look at what one could call a smooth conformal boundary extension. So that means we have a d plus one dimensional Lorentzian manifold with boundary m tilde g tilde. So this is what I've drawn here, and a conformal embedding iota, which embeds m into m tilde in such a way that the image of m under the conformal embedding is exactly m tilde without the boundary. Yeah, so all I do is I attach a smooth boundary to the spacetime. And similarly, I do have another conformal boundary extension m hat. And now the important assumption how you get some uniqueness is that you assume that you have a null GD6 gamma in the original spacetime, which has right endpoints in both of the other spacetimes. So in my terminology, I would say that you have a null curve which anchors both extensions. And so this is exactly the condition which allows you to get some uniqueness. So if we go back to this case, then you see that this exactly fails. Since, I mean, if I take these null GD6, the blue ones, then they do have a limit point in this extension, but they don't have a limit point in this extension. So here, they are not anchored by the same null curves. And so yeah, we assume that we do have this null GD6, which has an endpoint in both of these boundary extensions. And also, we assume that this null GD6 meets these 2 boundaries transversely. And then the statement is, there exist open neighborhoods around these endpoints, around p tilde and p hat, drawn here, such that if I restrict the identification map to these open neighborhoods, u tilde and u hat, that the identification map maps this brown region here to this brown region here as a diffeomorphism, and also it extends smoothly as a diffeomorphism if I also include the boundary. Yeah? And so this is exactly the statement that if I have these 2 smooth conformal boundary extensions, which are anchored by the same null curves, then I have that the extensions locally agree up to the boundary. So why do we, so let me first of all emphasize that this result of Piotr is much more general than what I want to talk about, in the sense that it looks at conformal extensions, while what I want to discuss later only looks at isometric extensions. So here in the result, there was a restriction that we have to exclude 1 plus 1 dimensional dimensions, 1 plus 1 dimensions, And this is exactly for the reason that Piotr also allows conformal extensions, so that there are explicit counterexamples to the statement in 1+1 dimensions. If you are looking at isometric extensions, as we will see, you can get rid of this, assumption. Also, let me say that while the theorem is formulated in the smooth sense, in the smooth setting, it does use null GD6, and so the proof, also as Piotr says in his paper, goes through two extensions which are at least C11, C11 log regular, and in order to make sense of this regularity at the boundary that you attach should be at least C21 log regular. And so the result that I want to present improves on the previous result by Piotr in two ways. So first of all, I want to find the best, the minimal or optimal regularity of the extension for which I can still get a local uniqueness result of the extension at the boundary. And the second, which might seem a bit more subtle, the second way in which I want to change the result is that I want to drop the a priori assumption that the extension which I have has already a smooth boundary. Yeah? This is something I also want to improve on. And the reason why I want to do this is that I want to apply this to inextendability results, where you would, so for example, here at the Cauchy horizon, I mean the weak null singularity at the Cauchy horizon is indeed a smooth boundary which is attached to the manifold. But you know, Piotr's result would only give you uniqueness of the extension if you already assume that another potentially other C0 extension also has a smooth boundary. So if I just start with another C0 extension, then I can't apply Piotr's result since I don't already know that it has a smooth boundary. So I want to start from general extensions and then infer that, you know, if I just have another extension, then it must also have in particular a smooth boundary and must be, you know, whatever C11 log equivalent or C01 log equivalent on the boundary. Let me now come to the main result. The one thing I should say, so I don't you know, I don't want to assume the smoothness of the boundary, but in order to get rid of this, I introduce another assumption which is not present in Piotr's result, namely that I only look at Lorentzian manifolds which are globally hyperbolic. So I'm mainly interested in Lorentzian manifolds which arise dynamically from the initial value problem, and so I look at globally hyperbolic spacetimes. And so this is the theorem, the first part of the theorem. So I start with a time-oriented globally hyperbolic Lorentzian manifold with at least a C1 metric. And then I look at two local Lipschitz extensions, m tilde and m hat. And again, I have this anchoring curve. So I take a curve gamma in M, which is a causal C1 curve, which has future limit points in both extensions. And then the first part of the theorem is exactly which gives me, like, again, a boundary across which I extend. And so this says that, you know, in the first extension m tilde, and similarly for the other extension, there exists a small chart around the endpoint of this null of this causal C1 curve gamma around p tilde, and the Lipschitz continuous function f tilde, which is a function from the, should think of the space-like component or space-like part of the chart into the time-like part of the chart. And this chart has the following properties, namely that it's centered at the point p tilde, and that all the points which lie beneath the graph of this Lipschitz continuous function f tilde, all those points are contained in the original manifold M. All the points on the graph, these are boundary points in the extension, and also that this anchoring curve is eventually contained beneath the graph of the Lipschitz continuous function. And similarly for the other extension. And so this is the cartoon of what I've just told you. This is our anchoring curve gamma. And here, this is this chart, U tilde, and here, this is the graph of the Lipschitz continuous function. The curve eventually lies beneath the graph. And here for M hat, I've drawn what could potentially also arise, namely that the manifold also lies above the graph of M. But this is something that could arise or could not arise. I don't care about this. So all I need is that below the graph, this is where the manifold is, and these are boundary points. And so you see that using the global hyperbolicity assumption, as I'll later explain, we have again found like a boundary of our spacetime, about which we now know that it's at least a local Lipschitz regular. So this is it allows rougher boundaries. Okay, and this is the main part of the theorem. So given this setup with these two boundary charts, we now know that there exist neighborhoods W tilde and W hat around these points, such that if I restrict the identification map to the region in W tilde that lies below the graph, that this maps this region diffeomorphically to the region here that lies beneath the graph, and that this identification map extends as a C11 log regular isometric diffeomorphism to the boundary. So here are a few comments in order. First of all, when I say it extends as a C11 log regular isometric diffeomorphism to the boundary, of course, is only local Lipschitz regular. So a priori, you can't make sense of a map being C11 on this local Lipschitz boundary. So this is, here we just use the standard definition of differentiable maps on bounded sets. So here what is proven is that the identification map extends as a smooth diffeomorphism from down here to all of omega tilde. So what I actually prove is that this identification map extends as C11 log regular diffeomorphism from omega tilde to omega hat. But what I've said before, of course, it only extends as a C11 log regular isometry to the boundary, and it's no longer an isometry above the boundary. What I also should say, so the theorem was formulated in the setting that the two extensions are local Lipschitz regular. If you have more regularity on the extensions, then of course you also gain more regularity of the extension of the identification map. So it's 1 degree more regular than the minimal regularity of the two extensions. So if both extensions are C2, then it extends as a C3 diffeomorphism. And I should also say that this theorem is sharp. So if the extensions are only Hölder continuous, then in general, the identification map does not extend as a diffeomorphism. And this is what I would like to talk about next. I would like to show you that if you relax the regularity assumption, then we lose the uniqueness of anchored extensions. And the counterexample is the following 1+1 dimensional cosmological spacetime. So here the t coordinate on 0 infinity and x coordinate on r, and this is our cosmological metric. And I want to construct two anchored extensions to t equals 0, which are not equivalent. And I do this in a similar fashion as before. So I construct two extensions by straightening out either the right going LGD6 or the left going LGD6. So here the first extension is that I introduce the iconal function v, which straighten out the right past right going null GD6, and to introduce a time coordinate tau like this. And in these coordinates, this metric here is of this form. And so you see that when tau goes to 0, tau goes to 0 when t goes to 0, that this here vanishes, but this is still a non-degenerate Lorentzian metric. In particular, I can extend it here just by setting this equal to 0 for tau less than 0. So I have a continuous extension, and I can construct another continuous extension by introducing the other eikonal function u and tau in the same way, and I get this metric by straightening out the past left-going null GD6. You can write down again the identification map. So here u expressed as a function of v and t in terms of tau takes this form, and you see that when t or tau goes to 0, this term here vanishes, since I have assumed that p is less than 1, so this is integrable. And so you see that the identification map extends as a C0 map to the boundary. Yeah? In particular, points that lie here in the boundary are also points that lie here in the boundary. But the identification map does not extend as a C1 map to the boundary. So if you look at the U component of the identification map and you differentiate with respect to tau, if it extended as a C1 map, then this should be in particular bounded. And you can see that this diverges as tau goes to 0, which shows that you have two continuous extensions. And I should also say that if I just extend this as by tau, by 0 when tau is less than 0, then these extensions are in particular Hölder continuous with exponent 2p over p plus 1, which can be made arbitrarily close to 1 if I choose p going to 1. So this shows that I've constructed two Hölder continuous extensions which are anchored by the same curves. Yeah, so these curves and these curves, they have both endpoints in the two extensions respectively, but such that the C1 structure of the extensions is different. And so what does that tell me, for example, about such weak null singularities? So it tells me that if I look at terminal weak null singularities, so singularities which have a C0 extension, then I'm tempted to ascribe some physical reality to this C0 extension. I say, okay, I can extend the metric or space and time in a continuous way to this singular boundary. I mean, we heard before, there are various attempts to construct ideal boundaries to singular spacetimes. But if we have a C0 extension, we actually do have something real, right? We do have like a C0 extension. And so in particular, you're tempted to say that, for example, if you have a time like GD6, which goes to the Cauchy horizon, for example, you could be tempted to say that, well, the velocity vector, the affine velocity vector of this time like GD6 remains finite at the weak null singularity, since its velocity vector is a finite vector, since I do have a C1 structure here. But exactly this kind of result shows you that if you talk about extensions, at this regularity, so below local Lipschitz, that this is something very subtle, since here in this extension, a time like GD6, might have a finite velocity at t equals 0. But here, since the C1 structure doesn't agree, in this extension, it could, while still maintaining a Lorentzian norm equal to -1, it could get infinitely boosted and approach a null vector. So this exactly demonstrates the a priori subtleness when you talk about low regularity extensions at weak singularities. So in the last few minutes, let me tell you some elements of the proof of the theorem. So this was the first part of the theorem, namely the part that guaranteed these boundary charts in which the boundary is manifestly a local Lipschitz graph of a function. And trivially, since we do have local Lipschitz extensions, I can moreover guarantee that in these charts, the metric differs arbitrarily little from the Minkowski metric in these coordinates. So this is why I said you can think of this as the space-like part and this as the time-like part of the chart. And also that the Lipschitz constant of the metric G tilde is uniformly bounded in this chart. So I don't want to tell you how to prove this. What I want to tell you is what could go wrong. And so one particular implication of having such a chart is that points on the boundary in the vicinity of this endpoint of this anchoring curve, that they can also be reached by time-like curves. Since recall, I mean, I had like C0 control of the metric. So in particular, just straight lines. These are time-like curve which lie in the original spacetime and end up at boundary points. So this is in particular a feature of having such a boundary chart. But this is actually something that crucially relies on the extension being local Lipschitz. So if I only had the assumption that the extension is continuous, then this could go wrong. And this you might, so there's an explicit example. I'll just give you here the cartoon of what could go wrong. So the spacetime M is the spacetime that is the region that is delineated by the dashed lines. And here again, the blue lines, these are future left-going null GD6, and the red lines are future right-going null GD6. And so here, this is the future null cone, and this is the past null cone. And so what we see, we can construct such a spacetime, and we can also construct a continuous extension of the spacetime. Here, all these right-going null GD6, they all meet at this point. This cannot happen for smooth spacetimes, but it can happen for continuous spacetimes. And so now if we look at a C1 time-like curve, we can construct one that starts here at this point, and then starts off here in this light cone, but always stays beneath the next red curve. So it goes like this and reaches this point over here. And so so this is, this could serve as an anchoring curve. So this is even a time-like C1 causal curve, which ends up at this point. But this point doesn't have any neighborhood that looks like this. Yeah, since in particular, the future boundary, this is this part up here. In particular, there is no neighborhood of boundary points which can be reached by time-like curves. Yeah, since here this is, if I wrote the boundary as a graph, would contain like this part and this part down here, but this part can only be reached by past directed time-like curve, not by future directed time-like curves. And this pathology here, of course, arises from the possibility that this time-like curve here might not be differentiable at the point at which it leaves the original space-time, or it might even be null here, or it might be null, as in this example. And this is, of course, related to the different class of time-like curves, as were first discussed by Chruściel and Grant in their paper. And so what you can show is that if the extension is at least a local Lipschitz, then you can deform such a curve gamma to a curve which leaves as a proper time-like curve, as a uniformly time-like curve at the boundary point. So this is why local Lipschitz is important. And so let me now say a few words about the next part of the theorem, namely the statement that once I've set up these boundary charts, that I can find small neighborhoods W tilde and W hat, such that the identification map is a diffeomorphism from here to here and extends as a C11 log regular map to the whole set, so from omega tilde to omega hat. And the first step, so this is the setup. I have this anchoring curve, and the first step I want to go over in this chart to a particular curve, namely just a curve of constant spatial coordinates, just a straight line. And I can do this in one chart, but then of course you have the fundamental problem I know that in this chart, the two curves have the same limit point, but what does this other curve do in the other chart? Does it also go to this point, or does it go to a different point on the boundary, or does it even leave the chart? And this is more abstractly a problem that you characterize when two inextendable causal curves, gamma 1, gamma 2, have the same limit point in extensions. And this is something which is solved using a construction, or characterized using a construction that actually comes from the B boundary. But given that I don't have that much time, I want to skip that. And so I just want to tell you that we can go over to this other curve, and we can show that in the other extension, this curve also goes to the same point p hat. And now the construction to control the differentiable structure all the way up to the boundary is the following. Namely that you choose here in one extension, you choose a space-filling family of curves. And here I can choose just the curves of constant spatial coordinates, so just straight lines in this chart, which just move in the x0 coordinate. And I take a transversal hypersurface sigma here. So a priori, I don't know exactly what these curves look like in the other extension. They could also, be well behaved and end up at boundary points which are close to p tilde, but they could also, a priori just leave the chart and don't end up at boundary points here. This is what I want to rule out. And so I take this transversal hypersurface sigma. If I make it small enough, I can also ensure that it's contained in this chart. And there I choose an orthonormal basis, E alpha, on sigma, and then I parallelly propagate it along this space-filling family of curves. So here in the one chart, I say I have x coordinates. In the other chart, I have y coordinates. And so this parallelly propagated orthonormal basis E alpha, I can write either with respect to the x coordinates in this chart or with respect to the y coordinates in this chart. As long as these curves along which I have this orthonormal basis, as long as they are contained in U hat, so where I do have the y coordinates, I can, from this orthonormal basis, I can infer what the change of coordinates is. Yeah, just by inverting. If I invert this matrix, bring to the other side, then I get control over the change of coordinates in terms of the coordinate components of these orthonormal bases in both charts. And so now the important bit is that since we know that both metrics are local Lipschitz, I do have these a priori bounds on G as well as on the Christoffel symbols. And then when you think about parallel transport, as long as Christoffel symbols are uniformly bounded, as long as the coordinate length of the curve along which you parallelly propagate the vector field is also uniformly bounded, then you can show that in these coordinates, the orthonormal basis also has bounded coordinates, and also the inverse. So by parallel transport and these a priori bounds on the metric, you can show that the right-hand side here is uniformly bounded, and so you get that the coordinate transformation is also uniformly bounded. And then you can use a bootstrap argument, since if you have this scenario in mind, then if you are restricted to a close enough neighborhood, then this scenario is only compatible with this coordinate transformation blowing up. Yeah, so if you stay close enough to the curve which is contained in both charts, and if you have uniform bound on the coordinate transformation, then you know that these curves must also stay close to the original curve, so you can rule out this scenario. And so to conclude this argument, with a little bit more work, you can not only show that this is uniformly bounded, but also that it extends continuously to the boundary and also in a non-degenerate way, so that this matrix is invertible. And also by the virtue of the map from X to Y being an isometry, you can boost regularity. And so you can show that this actually extends with more regularity to the boundary. And then you use classical extension theorems to show that this differential actually extends above the boundary. And so in this way, you get that you can find small neighborhoods such that the identification map extends as a C11 log regular diffeomorphism from one extension to the other extension. And so I think my time is up. Thank you very much for your attention. And this is actually global hyperbolic. Yeah. This is global hyperbolic. Yeah. So you can find a Chruściel hypersurface, which also goes there. Yeah. I mean, this is. I mean, you can find an extension, which extends across all of the boundaries of this global hyperbolic spacetime. And the issue is just that it's low regularity, so that you can have causal bubbles of some form here at this point. But the spacetime, the spacetime is perfectly well behaved. I mean, it's smooth, it's global hyperbolic, and just the extension is just continuous. Yeah. I mean so the proof to control the differentiable structure using parallel transport. This is something that should go through in the Riemannian case as well. The issue in the Riemannian case that I think you would have is that you don't have a priori control on the regularity of the boundary. So I mean, if I didn't assume global hyperbolicity, then the boundary could be very rough, arbitrarily rough. And like in the Riemannian case, I think you would need some condition that also gives you some starting control on the regularity of the boundary. If you somehow again make an assumption that there is a smooth boundary or sufficiently smooth, then yeah, you can do exactly the same in low regularity. But yeah, you would need some condition to rule out very, very rough boundaries. I mean, the why you also need the the regularity of the boundary is for the last. Sorry, I'm going the wrong direction. For the last part of the proof. So you can control the derivatives, of course, also independently of the structure of the boundary. But in order to actually extend as you know, a C11 log regular function, there you do need, you know, quasi-convexity of the boundary. This is, you know, just a property already seen if you want to extend functions in Rn. So if you have, you know, function in Rn, which is defined here, and you want to extend it up here, you need some regularity on the boundary. And you know, that there are results which show that you can extend if you have quasi-convexity, and, you know, in particular, like local Lipschitz is a quasi-convex case. So if the boundary is local Lipschitz, then you can extend as a function. But for example, there are counterexamples, you know, where you are in domains like this, you know, and this is something. If your function little f is defined here and you want to extend it to a function capital F on all the plane. And even if you have the seemingly regular situation that f extends as you know, a continuous function to the boundary, and also the derivatives extend as a continuous function to the boundary, this does not guarantee you that you get an extension in this neighborhood. And so even in the Riemannian case, when you can control the derivatives up to the boundary, it does not necessarily tell you that you can find that you can't extend the identification map sufficiently regularly.